Hello, I am Sampa Kuutti, and I'm here to present our work Adversarial Mixture Density Networks, Learning to Drive Safely from Collision Data. The motivation behind our work was the prevalence of supervised learning techniques such as imitation learning, where the model learns from a dataset of expert demonstration of the task. However, while imitation learning offers good scale into training data and good performance in scenarios similar to those seen in training data, these systems can often fail when encountering edge case scenarios not seen during training. In an autonomous vehicle, this could mean that when the vehicle encounters an edge case not seen previously, the control policy can completely fail to generalize and fail to drive safely. In worst case scenarios, these failures may lead to collisions. Therefore, to address this problem, we propose adversarial mixture density networks, which learn two distributions from separate datasets, which are an expert demonstration of safe actions and a collision dataset of unsafe actions. Our proposed use case is a highway vehicle following scenario where the host vehicle is an autonomous vehicle controlled by a learned control policy, and it aims to maintain a safe distance from the lead vehicle in front. All driving is constrained to highway speeds on a straight road without any lane changes. The aim of the host autonomous vehicle is to maintain a 2-second headway from the lead vehicle in front by controlling the gas and brake pedals of the vehicle with continuous control actions. The proposed adversarial mixed density network works by learning two different distributions, one representing safe actions and the second representing unsafe actions. The safe action distribution represents the correct action an autonomous vehicle should take to drive safely, which is learned through an expert demonstration dataset similar to typical supervised learning techniques. The unsafe action distribution represents the action likely to lead collisions, and it is learned from a dataset of collisions. This dataset of collisions was collected using learned adversarial agents, which were trained to create collisions with autonomous vehicle control policies, and in this way, a dataset of over 11,000 collisions was collected. The AMDN models each distribution as a Gaussian, which are parameterized by the mean and variance of the corresponding action. Each of the distributions are learned by the same model, where the separate branches are trained on their respective datasets, and the earlier layers of the network are shared for both tasks. To allow the model to learn a safe and robust control policy, we penalize the safe action distribution based on its similarity to the unsafe action distribution on the collision dataset only. This similarity is modeled by the KL divergence between the two distributions, which we aim to maximize. We utilize two different testing frameworks, which are naturalistic testing and adversarial testing. Naturalistic testing validates the control policy's performance in scenarios similar to those seen during training, and tests the driving performance in typical driving scenarios. For each control policy, we test the system for 10 hours of driving in the IPG CarMaker simulator, broken down into 5-minute episodes. The adversarial testing tests robustness of the control policy to safety critical edge cases by training new adversarial agents against the fixed control policy and comparing how many collision cases these adversaries can find. For each control policy, we train 5 new adversaries for 2,500 episodes, and the results are averaged between these 5 adversaries. The results from the naturalistic testing are shown in the table below. The table compares a feedback network trained to imitation learning, a density network representing a single Gaussian for the safe action distribution without any collision data used in the training, and 3 different AMDN variants. First, we see that the feedback network has very good performance in naturalistic driving with 0 collisions, a headway very close to the target headway of 2 seconds, and a minimum headway of 1.74 seconds. In comparison, the AMDN has 1 collision and a mean headway of 1.9 seconds, showing worse performance, while the first AMDN variant, which is AMDN without the KL divergence loss, has 2 collisions, showing worse performance than the 2 last models. The second AMDN model is the AMDN with the KL loss, where during inference, we sample the action from the safe action distribution. This AMDN model has 0 collisions in naturalistic testing, but a fairly low minimum headway at 0.9 seconds. In comparison, the last AMDN model is the same network, but here instead of sampling the action from a distribution, we take the safe action mu as the most likely action during inference and use this to control the vehicle. And here we see the results improve from the last model with 0 collisions and a minimum headway of 1.13 seconds. However, we can still see that the final AMDN, having comparable performance to the FFN model, but still a slightly lower height, showing slightly worse performance in naturalistic driving. However, comparing the results from the adversarial testing shows how effective these models are at handling edge case scenarios where collisions could occur. First, we see the FFN being fairly susceptible to these edge cases, with an average of 800 collisions, and the first collision happening in episode 245. In comparison, the AMDN has only 63 collisions, showing significantly better robustness to these adversarial scenarios. However, as we remember, this model has fairly poor performance in naturalistic driving, therefore creating a sort of trade-off between safe performance in typical driving scenarios and robustness to out-of-distribution events. Similarly, the AMDN without the KL loss only has 51 collisions in adversarial testing, but does not drive safely in naturalistic testing. Comparing the AMDN model with sampling action, we now have only one collision in adversarial testing, showing significantly improved robustness to edge cases and still maintaining a collision-free performance in naturalistic testing. The AMDN with the maximum likelihood action has even better performance with no collisions at all during adversarial testing and demonstrating similar performance to the FFN imitation model in naturalistic driving, therefore offering the best trade-off between reliable driving in typical scenarios and safe performance in rare edge cases. In conclusion, this work proposed an adversarial mixture density network approach for learning safe driving policies by learning two distinct distributions from two different datasets. The model does this by learning a safe action distribution from an expert driving dataset and an unsafe action distribution from a collision dataset. We showed that by penalizing the safe action distribution for its similarity to the unsafe action distribution in the collision data results in a safer control policy which is more robust to out-of-distribution events. We validated our approach in naturalistic driving environment and an adversarial environment. We demonstrated that our model has significantly improved robustness to adversarial safety-critical edge cases, whilst maintaining a similar performance in typical driving scenarios compared to typical imitation learning approaches. Therefore, these results demonstrate our model can improve the safety of learned control policies in autonomous vehicles. You can find further details about our work in our paper, and if you have any questions, you can leave me a question in the email address below.